Troubleshooting TCP/IP. The sections in this chapter describe common features of TCP/IP and provide solutions to some of the most common TCP/IP problems. The following items will be covered: TCP/IP introduction, tools for troubleshooting IP problems, general IP troubleshooting theory and suggestions, troubleshooting basic IP connectivity, troubleshooting physical connectivity problems, troubleshooting layer 3 problems, troubleshooting hot standby router protocol HSRP. TCP introduction. In the mid-1970s, the Defense Advanced Research Projects Agency DARPA became interested in establishing a packet switched network to provide communications between research institutions in the United States. DARPA and other government organizations understood the potential of packet switch technology and were just beginning to face the problem that virtually all companies with networks now have communication between dissimilar computer systems. With the goal of heterogeneous connectivity in mind, DARPA funded research by Stanford University and BOLT. Codes to create a series of communication protocols. The result of this development effort, completed in the late 1970s, was the Internet Protocol Suite, of which the Transmission Control Protocol TCP and the Internet Protocol IP are the two best known protocols. The most widespread implementations of TCP/IP is IPv4 or IP version 4. In 1995, a new standard RFC 1883, which addressed some of the problems with IPv4, including address space limitations, was proposed. This new version is called IPv6. Although a lot of work has gone into developing IPv6, no wide-scale deployment has occurred. Because of this, IPv6 has been excluded from this text. Internet protocols can be used to communicate across any set of interconnected networks. They are equally well suited for local area networks, LAN, and wide area networks, WAN, communications. The Internet Suite includes not only lower layer specifications such as TCP and IP, but also specifications for such common applications as email, terminal emulation, and file transfer. Figure 7-1 shows some of the most important Internet protocols and their relationship to the OSI reference model. As an interesting side note, the 7-layer model actually came about after TCP/IP. DARPA used a 4-layer model instead, which the OSI later explained to 7 layers. This is why this TCP/IP doesn't generally fit all that well into the 7-layer OSI model. Figure 7-1, the Internet Protocol Suite and the OSI reference model. OSI reference model and the Internet Protocol Suite. Let's start with the OSI reference model. Layer 7 application, Layer 6 presentation, Layer 5 session, Layer 4 transport, Layer 3 networks, Layer 2 data link, and Layer 1 physical. Now, the Internet Protocol Suite: FTP, Telnet, SMTP, SNMP, NFS, XDR, RPC, TCP, UDP, routing protocols, IP, ICMP, ARP, RARP, and not specified. Creation and documentation of the Internet Protocol Suite closely resemble an academic research project. The protocols are specified and refined in documents called Requests for Comments, RFCs, which are published, reviewed, and analyzed by the Internet community. Taken together, the RFCs provide a colorful history of the people, companies, and trends that have shaped the development of what is today the world's most popular open system protocol suite. The network layer, IP, is a primary layer 3 protocol in the TCP/IP suite. IP provides the logical addressing that enables communication across diverse networks. IP also provides fragmentation and reassembly of datagrams and error reporting. Along with TCP, IP represents the heart of the Internet Protocol Suite. The IP packet format is shown in Figure 7-2. Figure 7-2, the IP packet format, 32 bits, version, IHL, type of service, total length, identification, flags, fragment offset, time to live, protocol, header checksum, source address, destination address, options plus padding, data variable. The fields of the IP packet are as follows: version indicates the version of this IP datagram, IP header length, IHL indicates the datagram header length in 32 bit words. Type of service specifies how a particular upper layer protocol would like the current diagram to be handled. Datagrams can be assigned various levels of importance using this field. Today, this field is used primarily to provide quality of service (QoS) capabilities with TCP/IP for applications requiring predictable bandwidth or delay. RFC 2474 describes the method by which the TOS field is replaced by a DS field that is used to provide differentiated services. Diff-serve on networks. This field is split into two parts. The first 6 bits are used for the DSCP code point, which is used to differentiate traffic. The last 2 bits or CU are ignored by diff-serve compliance nodes. Total length specifies the length of the entire IP packet, including data and header and bytes. Identification consists of an integer identifying this datagram. This field is used to help piece together datagram fragments. Flags consist of 3 bits, of which the lower order bits control fragmentation. 1 bit specifies whether the packet can be fragmented. The second bit specifies whether the packet is the last fragment in a series of fragmented packets. Time to live maintains a counter that gradually decrements down to 0, at which point the datagram is discarded. This keeps packets from looping endlessly. Protocol indicates which upper layer protocol receives incoming packets after IP processing is complete. Header checksum helps ensure IP header integrity. Source address specifies the sending node. Destination address specifies the receiving node. Options allow IP to support various options such as security. Data contains upper layer information. Addressing. As with all network layer protocols, the addressing scheme is integral to the process of routing IP datagrams through an internetwork. An IP address is 32-bit in length, divided into either 2 or 3 parts. The first part designates the network address. The second part, if present, designates the subnet address, and the final part designates the host address. Subnet addresses are present only if the network administrator has decided that the network should be divided into subnetworks. The length of the network subnet and host fields are all variable. Today's internet does not segment addresses along classful bounds. It is almost entirely classless. The separation between networks and subnets has been effectively eliminated. The requirement to understand network classes and the difference between a network and a subnet remains solely because of configuration and behavioral issues with network devices. IP addressing supports 5 different network classes, and the high order far left bit indicates the network class. Class A networks provide 8 bits for the network address field. The high order bit at far left is 0. Class B networks allocate 16 bits for the network address field and 16 bits for the host address field. This address class offers a good compromise between network and host address space. The first 2 high order bits are 10. Class C networks allocate 24 bits for the network address field. Class C networks provide only 8 bits for the host field. However, so the number of hosts per network may be a limiting factor. The first 3 high order bits are 110. Class D addresses are reserved for multicast groups as described formally in RFC 1112. The first 4 high order bits are 1110. Class E addresses are also defined by IP but are reserved for future use. The first 4 high order bits are 111111. IP addresses are written in that decimal format, for example 34.10.2.1. Figure 7-3 shows the address formats Class A, B, and C IP networks. Figure 7-3 Class A, B, and C address formats. Class A 0 network host, Class 1, B 10 network host, Class C 110 network host. IP networks can also be divided into smaller units called subnets. Subnets provide extra flexibility for network administrators. For example, assume that the network has been assigned to Class B address, and all the nodes on the network currently conform to a Class B address format. Then assume that the dotted decimal representation of this network address is 172.116.0.0. All zeros in the host field of an address specifies the entire network. Rather than change all the addresses to some other basic network number. The administrator can subdivide the network using subnetting. This is done by borrowing bits from the host portion of the address and using them as a subnet field, as shown in Figure 7-4. Figure 7-4 subnet addresses. Class B address before subnetting. Class B10 network host. Class B10 network host subnet host. Class B address after subnetting. If a network address administrator has chosen to use 8 bits of subnetting, the third octet of the Class B IP address provides the subnet number. For example, address 172.116.1.0 refers to network 172.16. Subnet 1 address 172.16.2.0 refers to network 172.16, subnet 2, and so on. In today's world, the difference between subnet bits and the natural mask has become blurred, and you will often see only a prefix length that specifies the length of the entire mask. Natural mask plus subnet bits. It is still important to understand the difference between the natural network mask, which is determined by the network class, and the subnet mask, because writers sometimes make assumptions based on the natural mask of an address. For example, the natural mask of 10.1.1.1/24 is 8 bits because this is a Class A network, even though the subnet mask is 24 bits. Subnet masks can be expressed in two forms: prefix length, as in /24, or decimal notation, as in 255.255.255.0. Both forms mean exactly the same thing and can easily be converted to the other, as seen in example 7-1. Example 7-1. Subnet mask expressed in prefix length and decimal 255.255.255.0 is 111.111.111.000 is 24 bits counted once. On some media such as IEEE 802 LANs, the correlation between media addresses and IP addresses is dynamically discovered through the use of two other members of the Internet Protocol Suite, the Address Resolution Protocol, ARP, and the Reverse Address Resolution Protocol, RARP. ARP uses broadcast messages to determine the hardware media access control, MAC layer addresses corresponding to a particular IP address. ARP is sufficiently generic to allow use of IP with virtually any type of underlying media access mechanism. ARP uses broadcast messages to determine the internet address associated with a particular hardware address. ARP is particularly important to disk class nodes, which may not know their IP address when they boot. Internet routing. Routing devices in the internet have traditionally been called gateways, an unfortunate term because elsewhere in the industry the term gateway applies to a device with somewhat different functionality. Gateways, which we will call routers from this point on, within the internet are organized hierarchically. Dynamic routing protocols such as RIP and OSPF provide the means by which routers can communicate and share information about routes that they have to learn are connected to. This contrasts with static routing, in which routes are established by the network administrator and do not change unless they are manually altered. An IP routing table consists of destination address and next hop pairs. A sample entry, shown in Figure 7-5, is interpreted as meaning to get the network 34.1.0.0, subnet 1 on network 34. The next hop is node at address 54 and 34, 23, 12. Figure 7.5. An example of an IP routing table. Destination address 34.100.78.2.100. 147.9.5.0. 17.12.0.0. Next hop 54.34.23.12. 54.34.23.12. 54.32.12.10. 54.32.12.10. IP routing specifies that IP datagrams travel through internetworks one hop at a time. The entire route is not known at the outset of the journey. Instead, at each hop, the next destination is calculated by matching the destination address within the diagram with an entry in the current node's routing table. Each node involvement in the routing process consists only of involvement in packets forwarding packets based on internal information, regardless of whether the packets get to their final destination. In other words, IP does not provide for error reporting back to the source when routing anomalies occur. This task is left to other Internet protocols, such as the Internet Control Message Protocol, ICMP, and TCP protocol. ICMP performs a number of tasks within an IP network, internetwork, the principle of which is reporting routing failures back to the source of a datagram. In addition, ICMP provides helpful messages such as the following: echo and reply messages to test node reachability across an internetwork, redirect messages to stimulate more efficient routing, time exceeded messages to inform sources that the datagram has exceeded its allocated time to exist within the internetwork, route advertisement and router solicitation messages to determine the addresses of routers and directly attached subnetworks. The transport layer. The Internet transport layer is implemented by Transport Control Protocol TCP and the user datagram protocol UDP. TCP/IP provides connection-oriented data transport, whereas UDP operation is connectionless. TCP provides full duplex acknowledged and full flow control service to upper layer protocols. It moves data in continuous unstructured byte stream in which bytes are identified by sequence numbers. TCP can support numerous simultaneous upper layer conversations. The TCP packet format is shown in Figure 7-6. Figure 7-6, the TCP packet format. Source port, destination port, sequence number, acknowledgement number, data offset, reserved, flags, checksum, window, urgent pointer, absence plus padding, data variable. The fields of the TCP packet are described here. Source port and destination port. Identify the port sockets at which upper layer source and destination process receive TCP services. Sequence number usually specifies the number assigned to the first byte of data in the current message. Under certain circumstances, it can also be used to identify the initial sequence number to be used in the upcoming transmissions. Acknowledgement number contains the sequence number of the next byte of data that the sender of the packet echo expects to receive. Data offset indicates the number of 32-bit words in the TCP header. Reserved is reserved for future use. Flags carries a variety of control information. Window specifies the size of the sender receive window buffer space available for incoming data. Checksum provides information used to determine whether the header was damaged in transit. Urgent pointer points to the first urgent data byte in the packet. Options specifies various TCP options. Data contains upper layer information. UDP is a much simpler protocol than TCP and is useful in situations in which the reliability mechanism of TCP are not necessary. The UDP header has only 4 fields: source port, destination port, length, and UDP checksum. The source and destination port fields serve the same functions as they do in the TCP header. The length field specifies the length of the UDP header and data, and the UDP checksum field allows packet integrity checking. The UDP checksum is optional. Upper layer protocols. The Internet Protocol Suite includes many upper layer protocols representing a wide variety of applications, including network management, file transfer, distributed file services, terminal emulation, and electronic mail. Table 7-1 maps the best-known Internet upper layer protocol to the applications that they support. Table 7-1 Internet Protocol application mapping with common port numbers. Application and protocols. Application www browser. Protocols HTTP TCP port 80. The hypertext transfer protocol HTTP is used by web browsers and servers to transfer the files that make up the web pages. File transfer. The file transfer protocol FTP provides a way to move files between computer systems. Telnet allows the virtual terminal emulation. FTP TCP ports 20 and 21. Terminal emulation. The Telnet protocol provides terminal emulation services over a reliable TCP stream. The Telnet protocol also specifies how a client and server should negotiate the use of certain features and options. Telnet TCP port 23. Electronic mail. The simple mail transfer protocol SMTP is used to transfer electronic mail between mail servers and is used by mail clients to send mail. Mail Clients do not generally use SMTP to receive mail. Instead, they use either the Post Office Protocol version 3, POP3, or the Internet Message Access Protocol, IMAP. This will be discussed in greater detail later in this chapter. SMTP TCP port 25, POP Post Office Protocol 3, TCP port 110, IMAP Internet Message Access Protocol 4, Transmission Control Protocol TCP port 143. Network Management. The simple Network Management Protocol SNMP is a network management protocol used for reporting anomalous network conditions and setting network threshold values. SNMP UDP port 161. Distributed services, file services. X-Windows is a popular protocol that permits intelligent terminals to communicate with remote computers as if they were directly attached. Network File System, NFS. External Data Representation, XDR, and Remote Procedure called RPC combine to allow transparent access to remote network resources. These and other network applications use the services of TCP/IP and other low-layer Internet protocols to provide users with basic network services. Domain Name System, TCP/IP uses a numeric address scheme in which each node is assigned an IP address that is used to route packets to a node on the network, because it is much easier for people to remember names such as www.somedomain.com instead of 10.1.1.1. A protocol called Domain Name System, DNS, is used to map numbers to names, and vice versa. Most web pages refer to other web pages or links using these names instead of the IP addresses. This provides many advantages. For example, the address can change without breaking any links to a web page if the DNS table is also changed to point to the new address. Tools for troubleshooting IP problems. The tools ping and traceroute, both in the TCP/IP protocol suite, will greatly assist in troubleshooting IP connectivity. Most operating systems and IP implementations come with these tools installed by default on some Unix platforms. However, you may need to download and install a traceroute or traceroute package. Cisco routers provide the basic method of viewing IP traffic switched through the router called packet debugging. Packet debugging enables a user to determine whether the traffic is traveling along an expected path in the network or whether there are errors, in particular TCP stream. Although in some cases packet debugging can eliminate the need for a packet analyzer, it should not be considered a replacement for this important tool. Packet debugging can be very intrusive. In some cases, it can cause the routers to become inoperable until physical reset. In other instances, packets that are present on the network and switched through the router may not be reported by packet debugging. Thus, a firm conclusion cannot be drawn that the packet was not sent solely from the output of packet debugging. A network analyzer must be used to accurately make this assessment. Packet debugging should be used with extreme caution by only advanced operators, because it can cause the router to lock up and stop routing traffic. If not used carefully, the risk of using a packet debugger may be compounded by the necessity of disabling fast switching for packet debugging to be effective. As a general rule, packet debugging should not be used on a production router, unless you have a physical access to the router and are willing to risk it going down. Ping. This ping tool uses the ICMP echo request and echo reply message to test reachability to a remote system. In its simplest form, ping simply confirms that an IP packet is capable of getting to 2 and getting back from a destination IP address. Figure 7-7, this tool generally returns 2 pieces of information: whether the source can reach the destination and, by inference, vice versa, and the round trip RTT, typically in milliseconds. The RTT returned by ping should be used only as a comparative reference, because it can depend greatly on software implementation and the hardware of the system on which ping is run. If ping fails or returns an unusual RTT, traceroute can be used to help narrow down the problem. It is also possible to vary the size of the ICMP echo payload to test problems related to maximum transmission unit, MTU. Ping example, ping fig. .gif/CDR, Cisco RTR2, Cisco RTR1, Cisco RTR3, Cisco RTR4, Cisco RTR5, Cisco RTR6, 10.3.6.1/24. Example 7-2 shows ping returning three values, separated with a slash, the minimum, average, and maximum RTT. Large differences in these values could indicate network congestion on the network problem. In most cases, the average value accurately portrays the network latency to the destination. By default, ping uses small packets for connectivity testing. The packet size will influence the RTT values. The packet size may be changed in some implementations, including that of Cisco systems, iOS. Example 7-2, ping returning three values, separated with a slash, the minimum, average, and the maximum RTT. Cisco RTR1, greater than sign, ping 10.3.1.6, type escape sequence to board, sending 100 byte ICMP echoes to 10.3.1.6, timeout is 2 seconds. Success rate is 100%, 5-/5, round trip min, F, max 444 ms, milliseconds. Firewalls and routers can be configured to not allow devices to be pinged but to still permit other types of IP traffic. For this reason, a ping failure between two devices should not be misconstrued as a lack of IP connectivity between those devices. Table 7-2 shows a list of some of the codes returned by the Cisco ping utility, along with their meanings and possible cause. Table 7-2 Cisco ping return codes. Code meaning: each exclamation point indicates receipt of an ICMP echo reply. Each period indicates that the network server timed out while waiting for a reply. Possible causes: the ping completed successfully. The message can indicate many problems. Ping was blocked by an access list or firewall. A router along the path did not have a route to their destination and did not send an ICMP destination unreachable message. A physical connectivity problem occurred somewhere along the path. An ICMP unreachable message was received. A router along the path did not have a route to the destination address. An ICMP source quench message was received. A device along the path, possibly the destination, may be receiving too much traffic. Check input queues. An ICMP time exceeded message was received. A routing loop may have occurred. Trace route. The trace route utility sends out either ICMP echo request, Windows, or UDP. Most implementation messages with gradually increasing IPTL values to probe the path by which the packet traverses the network. See example 7-3. The first packet with TTL set to 1 will be discarded by the first hop, and the first hop will send back an ICMP TTL exceeded the message sourced from its IP address facing the source of the packet. When the machine running the trace route receives the ICMP TTL exceeded the message, it can determine the hop via the source IP address. This continues until the destination is reached. The destination will return either an ICMP echo reply, Windows, or an ICMP port unreachable, indicating that the destination had been reached. Cisco's implementation of trace route sends out 3 packets at each TTL value, allowing trace route to report routers that have multiple equal cost paths to the destination, and we will return back on chapter 7 page. What is the page number? It's page 7-12. Inshallah, ya Rabbil Alameen.